Hi everyone. In today's lecture, now we will look at variable oxidation states of transition elements, right? Variable oxidation states, right? These oxidation states are also known as valencies of transition elements, right? Here, this is your first transition series, right? And all these numbers below shows variable oxidation states of transition elements of first series, right? If you look at this scandium, it shows +2, +3. The oxidation states that are in bracket, they are rare or unstable, right? Second element has +2, +3, +4, and you can see manganese has all the way to +7 oxidation state, right? Zinc has +2 oxidation state, right? But other elements, compared to other elements like S block elements, P block elements, they do not have these many oxidation states, right? For example, calcium, which is an S block element, it has only +1 and +2 oxidation states. Sodium has only +1 oxidation state, right? So what could be the reason? Firstly, what do we mean by oxidation state? Oxidation state of an element is a state which is reached when a neutral atom will lose an electron, right? For example, if you have sodium, right, when sodium will lose one electron, it will form sodium 1 plus, right? Sodium 1 plus is the oxidation state of sodium which is reached when neutral sodium atom is oxidized, right? Loss of electrons we know is oxidation, right? So all these states resulted from, all these various oxidation states resulted from the loss of electrons, right? So basically loss of electrons will result into various oxidation states of transition elements. Now we need to know why, in order to understand like why transition elements can exist in variety of oxidation states, right? We need to understand why loss of so many electrons take place, or how loss of so many electrons take place in case of transition elements, right? So basically what we say is that transition elements exhibit various oxidation states or many oxidation states. Various oxidation states, right? Now various oxidation states like +2, +3, +4, +5, in case of manganese it is still +7. Now all these oxidation states are resulted by the loss of electrons, right? And we know that loss of electron take place from the outermost shell, right? And if you remember, the general electronic configuration of transition elements is n-1 d 1 to 10 electrons, ns 1 to 2 electrons or 2 electrons, right? Let's say 2 electrons. Now in case of transition elements, ideally these s electrons should get loose, right? Transition elements should lose only these 2 electrons which are in the outermost shell, right? So the maximum oxidation state it should be +1 and +2 after loss of these two ns2 electrons. But as we can see, it can show many oxidation states, right? And due to many oxidation states, it show different valencies in its compounds, right? For example, if you know, copper exists in 2 oxidation states, +1 and +2. +1 is cuprous, +2 is cupric, right? So you have CuCl and CuCl2, cupric chloride and cuprous chloride, right? So in both the compounds, this transition metal copper show different valencies, right? Why it shows different valencies? Because it can exist in various oxidation states. It can exist in 2 oxidation states. Like, this is what it means. Now, like I said, that ideally it should have only +1 and +2 oxidation states, right? Transition metal ions, but it shows lot many oxidation states. The reason is the energy. We say that oxidation state is reached when the element will lose outermost electron from the outermost shell, right? But in case of transition elements, the energy difference between ns and n-1 orbital is very less. Energy is almost same for ns and n-1 orbital. So same amount of energy, the energy which is given to ns orbital to remove its outermost electrons or to remove the electrons from this ns orbital, right? The same amount of energy would also be given to n-1 orbital, right? In order to remove electrons from n-1 orbital, you need to give it same energy, the energy given to ns orbital, right? So that is why it can show multiple oxidation states. For example, if we look at this Ti, right? Ti shows +2 oxidation states, right, which can be from ns2, but it shows +3 and +4, which has resulted by the loss of electrons from n-1 orbital, right? Let's take an example. Let's take the example of first element, which is your scandium. It's 3d1 4s2, right? Sc, electronic configuration 3d1 4s2, right? So +2 oxidation state is reached by loss of 4s2 electrons, right? And when this 3d orbital will lose its electron, because the energy that is required to remove 2 electrons from 4s orbital would be same amount of energy you need to give to electron in the 3d orbital, right? So this electron can be easily lost. So it will show, after loss of 1 electron from 3d orbital, it will show +3 oxidation state, right? First electrons would be removed from F4s orbital because this is outermost. Then electrons would be removed from d orbital of penultimate shell, 3d orbital, right? Similarly, if you look at Ti, the electronic configuration for Ti is 3d2 4s2, right? So first it will lose electrons from 4s orbital, right? And since same amount of energy needs to be given, so when it will lose 1 electron from 3d orbital +3, then 1 more electron from 3d orbital +4. That is why it shows 3 oxidation states, right? Now if you go to manganese, manganese has electronic configuration 3d5 and 4s2, right? 3d5 4s2. So +2 oxidation state after the loss of 4s electrons. Then it will keep losing electrons, right? When it will lose all the 4 electrons, it will show oxidation state of +7. When 1 electron it will lose from 3d orbital, it will reach +3 oxidation state. When 1 more electron, +4, +5, +6, +7. When it will lose all 5 electrons from 3d orbital, it will show +7 oxidation state, right? That is why manganese can show oxidation state till +7, because it has 5 electrons in 3d orbital which it can lose, right? Because energy that is needed to remove 4s electrons, the outermost electron, the same energy would be needed to remove 3d electrons, all the 5 electrons, right? So, and if you go to rest of the 5 elements, iron, cobalt, nickel, copper, zinc, right? You will see that oxidation states are now going less. Most common oxidation state is +2 and +3 in rest of the 5 elements, right? So it is not that you have to, you can remove all the 4 from all the elements. It's not that. The maximum oxidation state is equal to the sum of electrons in in n-1d orbital and ns orbital. It's not like that. The higher oxidation states in case of rest of the 5 elements, like +6 in case of iron, these are very rare, very unstable oxidation states, right? So common oxidation states would be +2 and +3, right? I hope till this point it is clear. So the basic thing, right, if you want to know why transition elements can show, or why transition elements show variable oxidation states, would be because energy required to remove electrons from n-1d orbital is same as ns orbital. Right? That is why it can show variable oxidation states. Now let's just understand, let's just look into some important points, right, related to oxidation states. Right? So here in case of transition elements, there is concept of minimum oxidation state and maximum oxidation state. Minimum oxidation state is due to the loss of these ns electrons, which is 2 plus 2, and maximum, like in case of manganese, can be +7. Right, when it will keep losing its n-1d orbitals. Now there are some important points related to oxidation state. Right, the most common oxidation state of elements in first transition series, you can see the most common is +2, right, and transition elements in lower oxidation states like +2 and +3 will form ionic compounds, right, and in higher oxidation states like +4, +6, +7, all these, it will form covalent compounds, right, like manganese has +7 oxidation state, so with oxygen it will form MnO4-. In this, all the bonds between manganese and oxygen are covalent, right, and that is why your elements, right, transition elements of first series or second series in higher oxidation states does not form cationic species, right? Why? It will not, the oxidation states, the elements of other series in higher oxidation states will not form cationic species, because in higher oxidation states it will form covalent compounds, right, and cations cannot form covalent compounds, right, that is the reason. Now we need to look into one important electronic configuration of zinc, right, this zinc. In case of zinc, you can see you have only one oxidation state +2. What is the reason? The electronic configuration of zinc is 3d10 3s2, right? So when zinc will lose 2 electrons, it will reach, after losing 2 electrons, zinc will form 3d10 electronic configuration, and this electronic configuration is a stable electronic configuration, right? After losing 2 electrons, zinc attains stable electronic configuration of 3d10. That is why it will not lose further electrons, right? That is why it shows only +2 oxidation state. So you may be asked in exams similar kind of question. Just remember, if you reach 3d10 electrons, 3d10 configuration after loss of electrons, then 3d10 is your stable electronic configuration, right? So it will become stable at this, will not lose further electrons. Now, some other important points are these oxidation states. The oxidation states increases with increase in atomic number, right? Oxidation states increases with increase in atomic number, or increases with atomic number in a group. When we talk about group, it's the group of the periodic table. Like if I continue in this group, below this manganese you have elements of 4D series, right? You have ruthenium below this, right? And the atomic number of ruthenium is higher than manganese, right? And ruthenium shows maximum oxidation state of +8, right? And whereas manganese shows maximum oxidation state of +7, right? So that is why it's like this: manganese, below it you have RH, ruthenium, right? Manganese has +7 oxidation state, ruthenium has +8 oxidation state, right? And atomic number of ruthenium is higher than manganese. So we say that with increasing atomic number in a group, the oxidation state also increases, right? Now, stability. If we talk about stability of given oxidation state of transition metal, that depends upon the nature of elements with which that it contains. In a compound, if we talk about the stability of oxidation state, then that depends upon the element with which it has combined, or the groups with which it has combined, right? And transition elements can form compounds. Transition elements can form compounds in low oxidation states like +1 and +0. If we talk about this compound, nickel NiCO, sorry, it's NiCO4, this compound, right? NiCO4, this NiCO4, in NiCO4, nickel tetracarbonyl, nickel exists in oxidation state of +0. Nickel exists in oxidation state of +0. So transition elements can exist in low oxidation states like 0 in case of nickel tetracarbonyl. Nickel is your transition element, right? Now the other important point is that highest oxidation states of transition metals are found in fluorides and oxides. Highest oxidation states of transition elements are found in fluorides and oxides. Why? Because fluorides and oxides are highly electronegative, right? When they are highly electronegative, they can extract maximum number of electrons from the transition elements, right? So that is why they show maximum oxidation states with transition elements, right? Because fluorides, fluorine and oxygen both are highly electronegative, right? So they can form maximum oxidation states, that is they can take maximum electrons from the transition elements, thereby resulting maximum oxidation state in transition elements, right? Now the other important thing is that stability of transition elements in aqueous medium, right, can be checked from its standard electrode potential, right? So we say that the stability of a particular oxidation state, right, in aqueous medium on the basis of can be known on the basis of standard electrode potential, right? This is your standard electrode potential. This is your standard electrode potential, which is your reduction potentials. This is standard reduction potential. When we say standard electrode potential, it by default means standard reduction potential, right? So if you know the standard reduction potential, or if you know the standard electrode potential, you can know the stability of the transition metal ion in aqueous solution using standard electrode potential, stability of transition metal ion can be known. Right, let's see how we can know the stability of transition metal ion using its standard electrode potential. When we say standard electrode potential, we mean standard reduction potential. Standard reduction potential means ability to accept electrons, right? If ability to accept electrons is high, right, then it will immediately accept electrons and will form neutral metal atom, right? Whereas if the standard reduction potential, or if the standard reduction potential is the ability to accept the electrons. If the value of standard reduction potential is low, that means the ability to accept electrons is low. That means if the ability to accept electrons would be less, that means the ion can exist in the solution. Right? It will not accept electrons and it can exist in the ionic state. That means that will make it a stable ion. Let's take an example of copper. We know that standard reduction potential of copper plus 1 is your 0.34, I think. No, I'm sorry, it's 0.52 plus 0.52 volt. Right? This standard electrode potential is standard reduction potential. This value shows the ability to accept electrons. Right? Whereas standard electrode potential of copper 2 plus is 0.34 volt. Right? So standard electrode potential value for cuprous is high and for cupric is low. That means cuprous, since it has high value of electrode potential, right? So that means since it has a high value for electrode potential, this Cu plus 1, since it has high value of standard electrode potential, it can easily gain electrons. To form neutral copper atoms. Right? So Cu2 plus will gain 1 electron to form copper. This will easily occur. Right? So your cuprous ions are less stable in solution. Because if you have cuprous ions in solution, they will easily gain 1 electron and will change into neutral copper atoms. Because the electrode potential value for cuprous ion is high. Whereas if we talk about cupric ions, the electrode potential for cupric ion is low. That means it has less ability to accept electrons and change into neutral copper atoms. Right? So Cu2 plus to gain electrons, this would be little difficult. Right? So copper ions, cupric ions can exist in solution. So they are stable in solution. Cupric ions are stable in solution. Right? I hope all this is clear. So the most important thing that we have understood here is why transition elements can exist in various oxidation state, because an amount of energy that is required to remove electrons from n-1 d orbital is same as energy required to remove electron from outermost ns orbitals. Right? So you can remove electrons with the same amount of energy, you can remove electrons from n-1 d orbitals. So that is why when electrons are removed from n-1 d orbital, it will show various oxidation states like we have understood it. Right? So I hope all this is clear. Thanks.